and welcome back to the Nanoscope. I'm your host, Kittrick Feinart, and this is your podcast for all things atomic theory. Now, last week, if you'll remember, we took my brother's time machine back in time and talked to the forefront of atomic theory, those that sort of started thinking about what the ultimate smallest thing in the universe could possibly be. And we found out that actually the real study of the smallest possible thing wouldn't get started till many years later. See, the Greeks just like to think about things without actually doing experiments. Then we talked a little bit about the alchemists who just sort of abused Aristotle's theory. They didn't really try to look any deeper into it. And then for a long time, atoms weren't really studied at all. We had the long era of the Roman Catholic Church that didn't really appreciate new scientific ideas. Then we had the Reformation, which pushed us along a little bit, got a little closer, and then Descartes and then philosophers in the 1600s finally got us there with the Enlightenment, when the study of science and the natural world was sort of ushered back into society. So, we pick up where we left off with the next person to look at what atoms really might be. So now we find ourselves, I believe, somewhere in the 18th century. Now, of course, I will step out for a moment and find someone who can tell me a little something about atomic theory. Alright, so, after following a bit of a rabbit hole, I have found someone who I believe can tell us a little something about atomic theory. So, sir, can you give me your name? I'm not even going to attempt to pronounce it.
Antoine Lavoisier. Yes, that is my name. Thank you, though. And you look English or something. Where are you from? What are you wearing?
Unfortunately, Mr. Lavoisier, that would take a little too long to explain. I just like a quick interview about what it is that you've sort of put forward into atomic theory.
Atomic theory. I do not quite understand what you mean, but I will tell you about my experiments. Yes.
Yes, that sounds wonderful. Just really, what did you look for the elements? Where did you find them? How did you discover this law of conservation of matter?
Oh, yes. That's all anyone wants to talk about. Now, okay, I will start where it really began in my mind. You see, we did an experiment. We had a glass jar. We put a small diamond in it, a small gemstone, and we put the jar. I measured it. I weighed it. I made it exact. And we put it under a huge magnifying glass, and we focused the sun onto the diamond, and it burnt away. But I weigh the jar again, and the jar weighs the same. The jar did not change weight, so the diamond was still there. It was still in the jar somehow, and I wanted to know why. There was no explanation. And so we do other experiments. I do an experiment. I burn phosphorus, I burn sulfur, I burn them in open air. And what results is heavier than what went in. Somehow there was more there. There was something in the air that the sulfur and phosphorus combined with somehow to make something new. It was in the air. So then we take the air. We break down the air into several different components. And I find oxygen. There is something in there called oxygen. It was not called this at the time, but that is what it came to be called. It combined with the sulfur, it combined with the phosphorus, and it made some acid, something heavier, something with the equal weight, just like the diamond. So then, after this discovery, we find something called mercury oxide, and when you heat it up, it gets lighter. But it releases oxygen. The same thing as before. It releases it in exactly the same weight as it loses. So I call this my law. It is the law of conservation of matter. Matter going in must be the same as matter coming out.
Wow. Thank you, Mr. Lavoisier. That is very enlightening. Now, while studying this, you didn't find any opposition from the church. Was there some religious reason you started pursuing and researching and doing science?
Oh, well, it was after the age of enlightenment, I suppose. Everyone was going about rushing around, their heads cut off, looking for something, some deeper science of the natural world. Voltaire, Jean-Jacques Rousseau, these sort of pushers of the Enlightenment, and even Francis Bacon and René Descartes before them. I mean, everyone was sort of pushing to find some natural order in the world. People didn't like to just push it off, say, "Oh, it's God. That's all it is. It's God every time." People wanted to find something more solid because of the Enlightenment. I really think, it got to me too. It's an infection. What can I say?
Well, thank you very much, Mr. Lavoisier. And actually, is there anyone else you could find? I'm looking to have as many interviews as possible.
Oh, yes, yes, yes. I know exactly who you need to talk to. Let me go get him.
Oh, all right. All right. Hello, Mr. Joseph Proust. Now, I can pronounce that one.
Yes, yes, Joseph Proust, that is my name. Now, what is it you want, Englishman?
Well, Mr. Lavoisier said that you came up with the law of definite proportions. I was just wondering if you could tell me a little bit about that and a little bit about where your inspiration for scientific discovery came from.
Oh, yes, finally, someone who appreciates my work. Now, you see, I look at oxygen. Because of my friend Lavoisier, you see, we know oxygen, we know metal. Metal cannot be broken down like other things. It is like an element. And so I look at these two, I see they combine in the exact proportion. You always have this many grams of metal for this many grams of oxygen. 10 to 1, 11 to 1. If I have 22 grams of this, I have 1 gram of this. So then if I have 44 of the first thing, I have 2 of the second. It is always in proportion.
Wow, that's fascinating, Joseph Proust. But how did you know the things were elements? How could you measure? How could you tell?
Well, this sort of gets back to your other question. You see, I stand on the shoulders of others. You see, I see the work of my friends, of other chemists. I see what is an element and what is not. They do that experiment. I do mine. You see, the same thing is true of my motivation. I look for science. I do not turn to God to answer all my problems. I want to find concrete answers to my problems. And so I search in science. I suppose it is because of the Enlightenment, but Lavoisier can tell you more about that. Thank you, sir. I must be going now.
Thank you, Joseph Proust. Thank you. Wow. Listeners, that was incredible. Straight from the mouth of the river, straight from where it came from. But I know you're all itching to hear from the grandpappy of atomic theory. So let's hop over to 18th century England and talk to John Dalton himself. So after a bit of searching, I've got him here. John Dalton, will you say hello to all of our listeners?
Hello, my name's John Dalton. You said you had some questions to ask me. I'm willing to answer any, but I do have tea in a couple of minutes, so I would like to make it quick.
I don't even know where to start, Mr. Dalton, but I guess with this. What impact did you have on atomic theory? And I know it's a big one, but can you sort of encapsulate everything that you did for atomic theory in just a couple sentences?
Yes. Well, I guess we'll start where I started. It started with meteorology, actually. I like studying the weather, studying how clouds move, rain and such. It was a fascination of mine, and I noticed that when you have two gases by themselves, the pressure they exert on sort of a jar that they're in or whatever apparatus they're inside of is not the same when they're put together. It's not a chemical solvent like we used to think. It's not all these gases chemically mixed together. They exert the sum of the pressures as if both are exerting pressure completely independently, and that wouldn't make any sense if they were some sort of fluid or a single object that flowed from one another. It would only make sense if it were tiny particles. So I developed a model to sort of to show what I was implying, and it was just as if all matter were these little hard spheres that would bounce and move, and they would exert pressure independently. It was the only way it would make sense. And so I started to do other experiments, and I ended up discovering a law of multiple proportions. You see, when you combine hydrogen and oxygen, and you combine them to form HO, which is water, and HO2, you will always the same ratio of the masses of oxygen implying that they are tiny, exact particles combining one by one.
So what you're telling me is that everything around us is just little particles bouncing around?
Oh, you laugh. That's what everyone else laughed at, but I looked it up. I researched it, you see. There was a Greek philosopher. His name was Leucippus. He had the same idea as me, and I think he's rather smart, and I'd say the same about myself. No need to get defensive, Mr. Dalton. I completely believe you. So, your atomic theory was little spheres, you said? Yes. Little hard spheres bouncing about in empty space, which is sort of exactly what Leucippus said. Although, of course, I wanted to research mine a little more rather than just think about it.
So if you had to say, John Dalton, after all your research, what were the properties of these tiny spheres? They were called atoms, correct?
Yes, atoms. Well, first I thought they were indivisible. They're the smallest possible particle. That is the only thing that could make sense, obviously. They were solid, and also each element has its own mass, unique mass of atoms. And you see, this is sort of the combined work of Joseph Proust and myself. We both sort of looked at the weight of the atoms going in and coming out of chemical reactions. And we knew they had to always be the same because of Antoine Lavoisier. It's all a combined effort, you know. And it's important to note that every atom is perfectly the same within each element, and each element's atoms are perfectly unique from each other in mass. Anyway, they're unique in mass, and so compounds are made with exact whole number ratios of two atoms of two different elements, and that's my atomic theory, really.
Thank you so much, John Dalton. Really fantastic. I will let you go for your tea. Well, listeners, looks like we have our first atomic model. A little sphere floating in space. So, that's where we are after the 18th century. Let's move a little further. But first, it's important to note that over in America, the colonies had fully separated from the British taxes and were now their own country with a fully separated church and state, which only encouraged chemists to dig even deeper into the laws of the natural world. So, next up, we have Amedeo Avogadro, about a couple years later than John Dalton. Hello, Mr. Avogadro. Now, can you tell me a little bit about how you improved on John Dalton's theory?
Yes, I did believe John Dalton. I thought his theory was fantastic. It was missing some things, and I pointed out to him through my own experimentation that when you have equal volumes and temperatures and pressures of gases, they must have the same amount of particles, if it is indeed particles, as John Dalton suggested. And indeed, when combined, hydrogen and oxygen needed 2-to-1 ratios to form an equal amount of water. You see, there are 2 hydrogen particles for every 1 oxygen particle in water. And so I was able to more accurately represent, using John Dalton's very own law of multiple proportions, the atomic weight of more particles. Gases, to be specific.
So, Mr. Avogadro, you would say that science really is a group effort?
Oh, yes. John Dalton and I worked together, and we really pioneered atomic theory, of course. He's the main granddaddy, but I like to think of myself as, well, his helper, who really established the true weight of many gases because of my observations of hydrogen and oxygen.
Well, thank you very much, Mr. Avogadro. And for everyone else, that wraps us up for this episode of the Nanoscope. Join us next week as we continue our quest through Enlightened Science to see what has become of atomic theory.
We know because of what I do. My experience.
The law of definite definite.
An Englishman. You Englishmen are swine.